All right, let's complete section 3.4. The example number 4 is asking us to graph the polynomial function, and here's the function given. Remember, step 1 is to find the x-intercepts. To do that, you take each of the factors here. This is to multiplicity 2, but we just write it down here, set it equal to 0, and we get x equals -2, so one of the x-intercepts is -2. Take the other one and set it equal to 0. This is a 0 factor property, and x equals 1 is the other 0. So when you start your graph, you're going to intercept the x-axis at +1 and at -2. Okay. Next, they ask us to find the y-intercept. To do that, I let x be 0. And when I put in a 0 into that f of x, I get 0 plus 2 to the third, 0 minus 1 to the second. So that's going to give me 2 to the third, negative 1 to the second, which will give me an 8 times a 1, which is 8. Okay, so we put a 0 in, f of 0 right here, and we got an 8. So at x equals 0, y is 8, right? Now, if we multiply this out, we know that is an x to the third. Let me double check that, yes. And that's an x to the second. So this is going to have a highest power of x to the fifth. So that tells us, since this is positive, that this end is going to be going up and this end is going to be going down. And now it's our challenge to find out what's going to go through the middle. If we cross through here and come back up, that's not going to work because the intercept is on this side. So this must be a turnaround point, and then we go back up to here. Now, does that make any sense? This is where x equals 1, and that is to the second degree. And we said today that if the 0 is to an even power, that it turns around at that point. It doesn't intercept it. Well, it intercepts, but it doesn't go all the way through. It turns around. Okay, and then we come back down, and it looks like it's going to go through here at -2. Let's look at this and make sure it's an odd degree. At -2, we have this factor to an odd power, so it should, in fact, go through. I drew another one of these. It's not much prettier, but there it is in case that's helpful. Okay, let's look at the next fill in the blank. If f is a polynomial function and a is an x-intercept on the graph, y is equal to f of x, then a is a 0 of f. A is a solution of f of x equals 0, and x minus a is a factor of f of x. All right, this is the intermediate value theorem. This is something will come up again in calculus. If f of x defines a polynomial function with only real coefficients, so only real coefficients, and if for any real number a and b, the value of f of a and f of b are opposite in sign, so one is positive and one is negative, then there exists at least one real 0 between them. So what they're saying here is that if you had a graph, let me see if I can zoom down on this because I know some of you will probably have trouble seeing it otherwise. Okay, if you have a point A, and let's pretend f of A is negative, and you have a point B, and f of B is positive. So that's what they're telling you to do. If you have f of A and f of B, and one is positive and one is negative, then somewhere between them, you are going to have a 0. It's going to have to intercept here because all the points here are something comma 0. Okay, and that seems pretty obvious. If one is positive and one is negative, if you had it here and here, somewhere in between it would have to cross. It would have a 0. Okay, that's the intermediate value theorem. Okay, I'm going to have to retape this arm here. Try to get it up. See if I can make it be still for a minute. Okay, that might work better. Okay, so let's look at the next example. Let me move these out of the way. Classroom example number 5. It says to locate a zero. Use synthetic division and a graph to show that f of x equals negative x cubed plus 2x squared minus 4x plus 5, that this thing has a zero between x equals 1 and x equals 2. Okay, the first thing we need to do is calculate f of 1. Plug 1 into there. So that's going to give us negative 1. Here, I'll just write it down here. Negative 1, positive 2, putting a 1 in there. Negative 4, positive 5. So that's going to be positive 7 minus 5 is 2. Okay? When x equals 1, y is 2. So that's a point on the graph. Okay? And now find f of 2. All right. So when you put in f of 2, you should get negative 3. Okay? And you can work that out or get your calculator to work that out. Looks like I had when I worked it out, a negative 8 and an 8 and a negative 8 and a 5. Yeah, that looks right. So that gave me a negative 3. So it goes through the point 2 comma negative 3. All right, so if you graph this, folks, and it goes through, let's mark it off to 3 on each direction. It goes through 1, 2, this function does, and the point 2, negative 3. Obviously, somewhere between those 2 points, right, it has to cross somewhere in there, right? We don't know if it's curved or straight. Well, I guess it's curving, right? We don't care really the shape. The point is it must have a zero by the intermediate value theorem. Okay? Since 0 is intermediate between positive and negatives, it has a 0 between x equals 1 and x equals 2. All right, that's all we had to do there. All right, we've got some more fill in the blanks. Get another piece of paper here. Okay. Let f of x be a polynomial function of degree n greater than or equal to 1 with real coefficients and with a positive leading coefficient. Suppose f of x is divided synthetically by x minus c, so we divide it with c. If the c is greater than 0 and all numbers in the bottom row of the synthetic division are not negative or non-negative, they're positive in other words. In other words, they are all positive, all of them. Then f of x has no 0 greater than c. Okay, so for whatever you tested, if you look at that bottom row of the synthetic division and everything's positive, then all the zeros will be numbers less than that, right? There's nothing greater than that that would be a 0. Okay. If c is less than 0 and the numbers in the bottom of the synthetic division alternate in signs, with 0 considered positive or negative as needed, then f of x has no 0 less than c. Okay, so if they alternate, then that no 0 is less than that, which means all the zeros are greater than that. Okay. And these are things you may have to write yourself little notes and kind of memorize these facts. They're helpful. So the first set of problems here, let me move this out of the way. Number 6. Part A. Show that the zeros of f of x equals x to the 4th plus 5x squared plus 3x minus 7 satisfy the following conditions. Part A, no real 0 is greater than 1. Okay, so we're going to try 1 as a 0. Now, when we put our coefficients here, we put a 1. Notice that we went from the 4th power to the 2nd power, so we have to fill the place for x to the 3rd with a 0, 5, 3, and negative 7. Okay? So we were going to try, that's a negative 7. There we go. Synthetic division, 1, 1, 1, 1, 6, finally something else, 9, 9, and 2. These are all positive. Okay? Since C is greater than 0, the number we're dividing by is greater than 0, go to this up here. It says if C is greater than 0 and all the numbers on the bottom row are non-negative, they're all positive, then f of x has no 0 greater than this. So these are all positive, so all zeros are less than 1. Or it has no zeros greater than 1. Okay, those say the same thing. It just matters how you want to say it. X equals 1, that is, right? Okay, so that's how you apply this. And that helps you to know where to guess, right? Start guessing numbers that are bigger than 1 when you're guessing what the zeros are. Okay? All right, part B. It's the same exact polynomial, and in part B, they ask us to prove that it has no real zeros. These only work for real. No real 0. 0 is less than minus 2. All right, so I'm going to take a minus 2 as my 0 and put it into the same lovely polynomial. Peeling the coefficients off the previous section. And let's work that. We'll bring down a 1, multiply, multiply again. Lovely. 23 remainder. Notice that these, it goes from positive to negative to positive to negative to positive. They alternate signs. In the remainder alternates signs, right? The bottom row of the synthetic division. And here we have a number that we're testing that is less than 0. So that's going to be the second case in this boundless theorem that tells us our bounds on the thing. If you have a C value less than 0 and the numbers in the bottom of the synthetic division, right down here, alternate signs. They do. They switch positive, negative all the way across. Then f of x has no zeros less than this. So it doesn't have any zeros smaller than this. No 0 is less than negative 2. Or another way to say that is all other zeros, all zeros, are greater than negative 2. Okay? It's the same. Either way you like to say it. And this falls out of the boundless theorem. Okay. Number 7. Am I going to work this one or what? Approximating the real zeros. Okay, let's look at number 7. I didn't actually do this the way I probably should have. I cheated. I will tell you a true confession. Plus 10. I suppose if I'm going to give you one of these, I'm going to have to state it like this to prevent you from cheating. I'm going to have to say, use the boundless theorem. Show that in this polynomial, no zero is greater than this or no zero, whatever. Okay, I expect I'm going to have to test you this way because otherwise you're going to do what I did on this one. And here it says to approximate the real zeros of the polynomial function. Now, I guess I did more than approximation here. I actually just used the polysolver. Let's look at that first. And when you do the polysolver on this, this is a third degree equation on, get out of there. Okay, get into the polysolver, go down to the third degree equation, select that, clear this out. My first coefficient is a -1. Go down to the next coefficient, clear it out, and put -8. To the next coefficient, clear it out. 4 to the next coefficient, clear it out. 10. Go down again. Solve if I typed it in right, which at least I typed it in the way I did before. The first solution, I'll call it x sub 1, is, let's see, -8.335939948, whatever, right? Okay, x sub 2, go down and see what the next solution is, 1.276048797. And the third solution is, and these are all real numbers, nothing imaginary here, -0.9401088484. Okay, and clearly I might want to tell you to round it, otherwise just put what you get on your calculator. We all have the same calculator. So with this polysolver, I came up with these zeros. I'm wondering if we have, I think what they intended for you to do is to use what you know about taking your P over Q, and we could start with 10, 10 over 1 or -10, plus or minus 10, plus or minus, we take the other divisors of this. There are only a few here. We could put plus or minus 5 and plus or minus 2 and plus or minus 1. I think are the possibilities. And then we start using these in synthetic division, and depending on what we get in the bottom row, we conclude and we try to zoom in on the zeros, right? So if we put a whatever, you just have to try some of these out. But again, if I want you to do this, I'll probably explicitly ask you this way. So that concludes it. I'm not going to do the last example on this. I'm not real happy with that one, and we're going to conclude it with this one. So you ought to be able to finish 3.4 homework before we meet on Wednesday. Hope you have a good week. Goodbye.